Thank you very much for the invitation from the organizers to present today. And I also wanted to just highlight the very last slide. I have a large number of acknowledgements, collaborators, but wanted to specifically point out Ido Berger and the Time Domain Group that's contributed a lot to what I'm going to present today, and also Dale Frail at the NRAO. So we've discussed a lot so far, kind of theory and observations, but I wanted to just come back to some of the motivating questions before I get into jets, because I feel like it's just very important to highlight these as we start thinking about some of the more intricate questions that arise in the observations. So are these actually a unique signpost of dormant supermassive black holes in inactive galaxies, or potentially smaller black holes? How does the occurrence constrain properties of these supermassive black holes, and what are the rates? Could this actually contribute to the buildup of supermassive black holes? And what is the environment like around them? And I wanted to just highlight here, there still is this sort of big open question with intermediate mass black holes. So potentially, anyway, you see the gap there. Looks like I should be using this one. So potentially, if we actually had tidal disruption of white dwarfs around intermediate mass black holes, this is something that we could actually probe and start to fill in. Some more kind of motivating questions include, how do jets actually turn on? So as was mentioned in the first talk, active galactic nuclei are on for millions of years. We don't actually get to see a jet turn on for the first time, which we potentially get to see in tidal disruption events. And what's their composition? How are these jets actually powered? Can TDEs actually explain variants of gamma ray bursts, including the ultra-long class? There's been some kind of a flurry of papers recently on this. Could they be a source of ultra high energy cosmic rays? Could they provide a fuel source for quasars? And then I think there's sort of an open question in terms of distinguishing between TDEs and AGN. I mean, there's huge variability in the AGN population, so there's probably some confusion between the two, or some overlap that we want to think about. As Suvi also mentioned, there's questions related to the reprocessing of emission off of this kind of 2 to the minus 5/3 line. And this was kind of mentioned very briefly, but just wanted to highlight for those that haven't seen this or thought through it. This is a slide from Linda Strube. And so if you basically assume a Keplerian potential and you do one single derivative, you can easily find that you should have a mass fallback rate of to the minus 5/3. And so then if you assume that that mass translates to luminosity, that's where you get that expectation. So it's a very simple, something you could do with undergraduate students to calculate this. One other thing that I just wanted to highlight, again, is the importance of what the tidal radius actually is, depending on the mass of the black hole and the star being disrupted. So for a solar mass star and a 10 to the 6th sort of black hole, you sort of maximize in this range your tidal radius. So that's kind of why that's been emphasized in the literature, kind of black holes of that range. And you see if you go up to 10 to the 8th or 10 to the 9th, pretty soon you're going to swallow stars whole. So that's kind of why this is focused on. But if you're looking at smaller stars or even planets, you can actually probe the lower end of massive black holes. So just wanted to sort of emphasize this very clearly to keep in the back of your minds. And then, some other questions come down to the black hole properties, like spin and GR effects that were discussed in the first two talks, and as Avi asked in the last session, binary black holes, because it actually is very difficult to get a star close enough to a black hole to be disrupted. If you look at the population of stars around Sagittarius A star, it's difficult, but if you had a binary black hole, it could potentially be easier. So a quick overview of what I'm going to talk about today is what the theoretical predictions were for jets in tidal disruption, then go through some observational evidence and really focus on the one event I've worked on mostly, and then a few other events that have been discovered since then. And then a little more discussion about some of the theoretical considerations that inform some of the questions that I mentioned to start with, and then what the future is. So I know I'm standing between you and lunch, so if you forget everything else, do remember, just like everything else in astronomy, there's two main types. So to the left, we sort of have the picture that James presented, where you have tidal debris, and it's kind of in the plane being disrupted. But this new picture is actually launching a jet perpendicular to the plane of the disruption. So starting in the early 90s, all the observations were in the soft X-rays, UV optical flares, emission line transients is how people expected to actually see tidal disruption. The change was Swift discovered events that we now believe are jetted, but it really was detection of radio emission that was able to solidify the fact that we were actually seeing a jet moving at relativistic speeds. So what were the theoretical predictions? So if we go back to sort of the late 70s, a lot of the predictions, as Suvi and James mentioned, were looking, UV soft X-rays. If you look at some of the early work by Frank and Rees, potentially 2 consecutive supernova-like events. So if you actually think about the star being kind of squeezed as it's on its way towards the black hole, maybe we would actually see something like a supernova. Time variable H-alpha emission from various numerical simulations. But one thing that I think is really important to highlight as we're talking about jets, so actually in 2010, there was a prediction by Dimitrios and Bryan that there should be radio emission from kind of ultra-relativistic moving material. And it's interesting because this was predicted, but it hadn't actually been kind of fleshed out theoretically. So Stephanie Camosa and her team, with some of the X-ray flares that had been discovered, they did actually go and look for radio emission, saying like, hey, maybe we'll see it, similar to AGN. They found no radio detections. So this is a paper Stephanie had from 2002. There was one source that had some radio emission, but it was actually resolved emission, and it kind of had AGN activity in that particular source. But everything else, to the limits they looked at, no radio detections. So this particular paper by Dimitrios and Bryan, it's interesting because the final published version is after the Swift event, but they actually posted it to the archive a month before, which is really, really amazing. So it basically was looking at the same formalism as you would expect from a gamma ray burst, so very similar to what Rem talked about the very first session of this conference. So as you have material moving out into the interstellar medium, you would expect there to be sort of a forward shock, a reverse shock, and as this medium interacts, you're going to get a bright radio transient. So they actually thought, in most cases, we're going to be looking at a line of sight not directly down the barrel of the jet. So we would expect to see radio emission at a time scale of about a year after a tidal disruption event occurred. So one thing I wanted to show that's actually interesting, and I'll go into a lot more detail of these observations, but the first event where we actually do have evidence of a relativistic jet, the Swift source, 1644 plus 57, their prediction was made at about 20 gigahertz. And this plot below is from a kind of overview of TDEs that Stephanie published last year. And so the red curve actually shows the 15 gigahertz light curve that was done by Guy Pooley with the AMI large array in the UK. And it did peak, at about a year. There's lots of kind of variations and nuances, but it's really interesting to see, again, as Suvi said, theory actually came before the observations in this case. So again, just wanted to kind of highlight the state of things. If we look at sort of discoveries of TDEs as a function of time, you can actually see basically through the early 2000s, these were all kind of the optical soft X-ray, and it was basically in 2011 when Swift came online that the first jetted TDEs were discovered. And again, wanted to point out kind of the steep rise in the number, and also wanted to point you to a TDE catalog that James is maintaining similar to the open supernova catalog. So this lists all of the potential TDE candidates, and there's, I believe, 65 or 66 candidates to date. Of those, 14 or 15 are heavily contested, may not be TDEs. But of those, it's actually interesting that there is a fraction that's maybe roughly 10% that may be jetted, may have outflows. And these include Swift 1644 plus 57, another one discovered basically just weeks later, and then 3 others that I'll kind of mention moving forward. And so this 10% fraction of TDEs that potentially launch jets quite a bit of work has been done on this. Jeff Bauer actually looked at a number of potential TDEs and looked at which had radio observations, and this is from a paper that he wrote, where again he found that roughly 1 in 10 had some affiliated radio emission. But you'll see, it gets a little bit more complicated when you start looking at the details, and so we'll get into that. I wanted to highlight a little bit, we're kind of in a really special era right now when it comes to radio observations and these transients moving forward with optical surveys and the wide field high energy. You get a lot from the radio, not just evidence for kind of relativistic expansion if you see self-absorbed synchrotron emission, but you also can get localization, information on the circumburst density at extremely, extremely good angular resolution. And then also magnetic field strength from polarization. And this is possible. So if you look at a lot of the early detections in the radio, this was before the VLA upgrade. So if you just look at sort of the change in sensitivity and bandwidth over the last kind of 5 years as this upgrade has been completed, you see that we really have a great opportunity with a lot of the surveys to take advantage. And so I think this has made a difference. So now I want to spend about 10 minutes going into more detail in SWIFT 1644 plus 57, because we have such a great kind of wealth of multi-wavelength data to kind of get a picture, and then I'll kind of present the other ones that have been detected after this, and then you kind of look at for comparison. So this was discovered by SWIFT March 2011. Initially, it was thought to be just a normal gamma ray burst, but it was very unique in the fact that it had multiple gamma ray triggers that was not normal for a long gamma ray burst. Then once these triggers happened, typically things might last 100, a couple of thousand seconds, maybe a little bit more for the ultra-long GRBs. But the X-rays actually continued for a long time, and people very quickly saw that the fall-off of the X-rays actually roughly followed T to the minus 5/3. So, even without any other data, this was already starting to hint at the fact that maybe this could actually be a tidal disruption event. Then we had embarked on a full radio campaign, actually just thinking it was a gamma ray burst, but very quickly, you could see that it was something different and something special. So we were able, you can see on the far right, that's the host galaxy, which was an ordinary galaxy. The spectral lines showed kind of no evidence of AGN activity. The dashed circle shows the SWIFT XRT error bar. So it would be hard to know exactly where it was coming from. But with VLBI observations, we're able to pinpoint kind of the radio emission coincident with the center of the galaxy, and subsequent observations have been done that also confirm that. So that was good because it was able to link this high energy transient with the center of this kind of normal inactive galaxy. And then also through equipartition analysis of the radio observations, it was able to link in time with the time of the trigger of the high energy trigger. So that was also very telling. So the radio monitoring campaign, we actually initiated a few hours after the event, and we're very fortunate that kind of had things set up to run from less than a gigahertz all the way up to 345 gigahertz. And I would point you to the SMA actually contributed some really beautiful observations less than a day after, and Glenn has a poster that shows some of those observations. So all the data is published for the first 3 years. We actually still have observations ongoing. And I also wanted to highlight there's full polarization calibration after about several weeks after the event was discovered. And this is actually extremely interesting when you think about the physics of the jet and what might be expected if you actually have this jet processing in some ways. And I'll just say that there's some hints that I think the polarization may be able to speak to this. But again, that was only possible because of the VLA upgrade, being able to have, the sensitivity we needed to actually get linear polarization. So how did we actually know that this was synchrotron emission. Here you actually see the light curves at various frequencies. So the radio, high frequency on the top plot. The bottom right plot, you see overlaid the X-ray at the same time. And so the X-ray was highly, highly variable, while the radio was kind of slowly increasing. So this initially pointed to the fact that these are coming from two distinct regions in the source. We did very simple modeling to start with, but since then there's 4 or 5 papers that have gone back and done very, very careful, more elaborate models. But basically, you can demonstrate a relativistic outflow with the Lorentz factor of a few by assuming equipartition, making a spherical assumption of sort of the outflow, and then you can calculate the equipartition size. And so you can actually see here sort of the SED changing as a function of time. The radio is all on the left. And it's interesting to point out on the far right, that's the X-ray, and those are not actually error bars. That's actually the variation in X-rays in the early kind of seconds after the burst. So wildly variable. And I think theorists are still not entirely sure what was leading to this wild variation sort of in the X-ray flux. So again, as I said, the radio spectrum was a synchrotron self-absorbed spectrum, very similar to what we get in gamma ray burst. There were optical limits showing about 3 magnitudes of absorption. So there's one hint of sort of an optical detection at very early times, but basically no optical after that. And the X-ray luminosity exceeded the synchrotron by about a factor of 1,000. So you can make some very basic arguments about what the beaming angle would have to be of this ejecta. So again, how did you know that it was moving relativistically? So on the left side is just a simple plot showing, at each epoch calculating what the equipartition size would be, and then you can work backwards and see that you would then expect a size of 0 that was coincident with the time of the high energy burst. But then a whole separate line of reasoning, not even taking that into account, is looking at certain radio frequencies you expect scintillation from our own galaxy. And so you expect more to happen at about 10 gigahertz than the higher frequencies. And sure enough, if you remember kind of the curves I showed, we would see sort of scintillation in the radio at early times, so you can draw conclusions about limits on the size of the source based on the scintillation. So this is again very similar to what Rem discussed in the first day. So this was, a great opportunity, as I mentioned, to not just, once you see that there's actually a jet moving, now you can learn a lot. This was probably a quiescent black hole prior to this event happening. So can we actually study the density structure around this black hole as this jet propagates and learn something about that environment that you couldn't learn otherwise? So we started modeling at each individual epoch separately, and as Suvi said, there were surprises along the way. So things basically look to be following exactly expectations for modeling that we would do for a gamma ray burst, where there's a single ejection event and you kind of monitor it. And so we kind of made predictions, and the blue lines were kind of what was predicted if you just sort of assumed a simple evolution in time. And so the dashed line is what was expected. But around 30 or 40 days, it seemed like there was actually an increase in energy. So things all of a sudden started to increase instead of decrease as expected for kind of one single impulsive event similar to a gamma ray burst. So this was a puzzle. Was this an increase in energy in the source? Was this some kind of structured jet? Was there a density enhancement? Was there kind of a second wave of the star that was accreted that led to this? It led to a lot of questions, like why this actually happened. So again, that was around 36 days when that increase happened. And so, typically with gamma ray burst, we may not have enough data points to actually model each epoch independently, but we did have the full spectrum, and we're able to model it at each epoch and did not have to actually propagate forward in time. So that was a mystery, and I'll kind of go back to this when I discuss some of the things that theorists have come up with later. One other thing just wanted to mention again is, from the radio emission, you kind of get a combination of energy or density. So from that, we were able to look at what the density was sort of around this black hole, and it's really fantastic that we can actually do it better than our own Milky Way galaxy, unless there's a cloud that's ever disrupted, then we might have a chance. So that's actually worth noting, and that was done, again, with the assassin event. So now kind of moving to the present day, here again, it was the X-rays as a function of time falling off, and all of a sudden, the X-rays just plummeted. And so one thing that was really interesting, this X-ray was, you can find in an ATEL by Andrew Levon and Neil Tanvir. And so one thing we did is look at what would be the expectation of the X-rays if you followed the synchrotron tail all the way to the X-rays. And so that would be all the way down kind of where this X-ray point was. But then, is that actually true, or is there some underlying disk? What can we learn about the X-rays at this point? So I think this is still an open question, but there's been a number of observations following up. So there's various models, what we would expect from the X-rays. So I'd point you to this paper by Levon. And I also would want to point you to the fact that the second event discovered by Swift that Brad Sanko and collaborators worked on found very similar behavior. So radio emission, they also saw the X-rays fall off like t to the minus 5/3, and this also steep drop at about the point where you would expect the Eddington luminosity to drop. The accretion rate to drop below the Eddington luminosity. And then there's actually a third event that I've overlaid here in 2015 discovered by Swift, where you see kind of a similar decline in the X-rays. But I believe they don't have observations that extend beyond that point. So one thing that I just wanted to kind of alert us to is the fact that, maybe we'll actually see a jet turn back on at some point when we get to very sub-Eddington, and also to the fact that Fabio and Enrico had actually kind of predicted this time scale when we would actually fall below the Eddington rate. So there's a number of kind of theoretical variations that we would want to consider. So some people have looked at sort of a full relativistic equipartition treatment. We didn't do the full relativistic treatment in our original papers. And so there's a potential for a change in the microphysics. So there's possibility or suggestions that there could be inverse Compton cooling. Additionally, folks have done detailed hydrodynamic simulations. There's also, as I mentioned, suggestions that maybe this is the longest gamma ray burst. So I had put tidal disruption events in quotes on the very opening slide because we kind of assume this, and we've ruled out lots of things, and I think the evidence supports it, but I think we do want to be open to other options. Additionally, due to the kind of rapid variation in the X-rays, was this actually a solar mass black hole that was disrupted, or was it a white dwarf disrupted by an intermediate mass black hole? And then there's also recent work showing that maybe this is a two-component jet. So there's a whole flurry of work kind of theoretically that kind of explains various aspects or things that are intriguing about these observations. Now, real quickly, just wanted to mention Assassin 14Li. There's been a lot of discussion. This one is really interesting because, unlike Swift, it was detected in optical and X-ray, multi-wavelength, and it's very, very close. Again, our group, as well as Shewart, had some radio observations. We had broadband across multiple wavelengths, and this shows kind of where the energetics put this event compared to the Swift event and the second Swift event that we think have jets. So this one seems to have an outflow. And I wanted to point you to, Kate Alexander has a nice poster that kind of goes through this, but this paper shows a non-relativistic outflow, kind of 12 to 36,000 kilometers per second. There's also suggestions that this could be a thermal tidal disruption flare. Folks have seen infrared emission from a dust echo, so this is the recent paper Suvi mentioned. And then there's also suggestions that maybe the radio emission doesn't actually come from a jet perpendicular, but it's actually the debris tail kind of returning in the plane, and it's sort of that interaction that is leading to the radio emission. In just the last minute, I want to skip ahead to the question of off-axis events. So point you to, we ran a number of simulations with the NYU Afterglow box fit, so using just the basic parameters for gamma ray bursts, and you can say, well, what would be expected if you're looking at something off-axis? So this was a source from Panstar, written up in a paper that Ryan Chornock wrote. And so this is something that we can do for all kinds of sources. You would expect on a time scale of a couple years for, if there is some kind of outflow, to be able to detect radio emissions. So this is something we want to go back and look for. There's a number of sources that our group is doing this for. So there's 2 super Eddington sources, the Dougie event and another Assassin 14AE. And then the corona line emitters that were mentioned, we also are doing radio observations, and Kate is leading that. So then let me just skip ahead real quick to the future. Again, there's going to be a lot of optical surveys kind of pointing out candidate events. This is work from Stewart showing that maybe colors will be one way to look for this. And that, ALMA is going to have the sensitivity that, at a week or 2, we might be able to actually detect things that we weren't able to with the SMA or KARMA. This is just showing kind of the sensitivity of ALMA compared to sort of the pre-existing arrays. We also have the VLA Sky Survey coming online, so this is a good possibility. But I did want to just sort of in the last 1 minute point to the fact that detection rates are going to be tough, I think, with optical and radio working backwards, because for these jetted events, they peak at high energies first and then kind of transition. And with scintillation and other things, it's going to be hard to kind of pull out all of this information. So we'll be able to get things like rates, but it's going to be very difficult, I think, to do as detailed of modeling in this way. So I think for the future, it's very important to also have the high energy kind of wide field things like SWIFT. So I'm looking forward to Neil's talk to hear kind of what the future is there. And then wanted to end with the acknowledgements. Again, there's this great review paper by Stephanie, and point you to the catalog of potential tidal disruption events that James has organized. Thank you.
I just wanted to clarify, when you say there's 2 types or there's only 10% seen, this is just an observational or off-axis effect, right? Or is there fundamentally something that you believe is different about ones that produce jets?
No, I think that there is something fundamentally different. So James alluded to this in the fact, if there's actually super Eddington accretion, it looks like so far those are the ones that we've actually seen jets. Of course, if there is super Eddington accretion and you're off axis, you're not going to see it, or you'll have to wait a long time to actually see the jet spread. There are the cases, so Assassin 14LI, it looks like there's some kind of outflow, but it doesn't look relativistic. And if you look at sort of what the expected accretion rate is, it isn't super Eddington. So it does look like there is actually something going on there.
The first SWIFT event, 1644, had a lot of variability in the afterglow phase, and I don't think the other 2 had as much. I don't know if you have any comments about, what's causing that and why they might be different.
Do you mean in the X-ray or in the radio?
In the X-ray, I'm sorry.
In the X-ray.
Yeah.
As far as I know, people have looked into it, and I do not have a good answer for that.
So we're expecting a kind of smooth decay, and there's more flaring than you might expect.
Mm-hmm.
So the one great advantage of jets is that we can see them all the way to the edge of the universe. So the TDs usually are observed just like supernova. They can be up to redshift 1 and so. But with jets, we can see AGN jets out to redshift 5, 6. Do you foresee that as a way of finding TDs at very high redshifts? And if so, how detectable, how high can the redshift be if you were to take one of these templates? Another way to phrase it is how easy it is to detect the one that you found, and how much farther can you see them?
So I haven't calculated the rates, but I would point us to an analogy of gamma ray bursts, right, which have been detected up to a redshift of 8 to 9, depending on what you believe. And so, these things are clearly as bright, a little bit longer lived. So, yeah, I mean, I think there is strong potential for that.
So that could be a way of tracing the black hole history at very early times.
Especially if the rates are different than what you might expect.